What we're going to talk about from here on out are laws and theories of science that have been proven over the years. So the scientific method has been done over the years to prove that what we are talking about in this course is in fact correct. So we're going to start with the phases in the classification of matter. We first have to understand matter before we can do anything with it. So all matter can be classified as either a pure substance or a mixture. A pure substance or a mixture is what matter can be classified as. When I say pure substance, well, a substance is a form of matter that has definite composition and distinct properties and is made up of atoms and molecules. Examples of this include salt, iron, water, carbon dioxide, and so many more. I encourage you to think of your own examples of what a substance could be, because it really is anything that we have in our natural world. The soap that's at our sinks, the milk that's in our fridge, those are all substances that we can then classify as either a pure substance or a mixture. All substances can be classified into three different phases. Our three different phases are solid, liquid, and gas, which I have shown here in this image, where solid has a fixed shape and volume. Liquid takes the shape of its container and also has a fixed volume, whereas a gas expands to fill whatever container it is in and therefore has the volume of that container. If gas is not in a container, it does not have a fixed volume. So let's go into pure substances a little bit more. Pure substances can be broken down into two different types, an element or a compound. An element is a pure substance that cannot be broken down into simpler substances by chemical changes. Okay, it cannot be broken down. So this is typically one type of element. It's usually not a molecule that's made up of multiple elements. So our elements that I have, for example, here are gold, phosphorus, and oxygen, where next to them in the parentheses I have their chemical symbol. Now these are just three examples. We know that we can find more elements on our periodic table. So if you don't have a printout of your periodic table yet, I would strongly suggest getting one of those, printing one out from the internet or from our e-learning course, and having that with you, because we will be using that very often in this course. And that way you can see all the known elements in our natural world. A compound, on the other hand, is a type of pure substance that can be broken down into simpler substances by chemical changes. So when I say chemical changes, we typically mean breaking of bonds. So compounds are typically made up of two or more types of elements that are chemically bonded. So examples of this would be water, H2O, which I can draw here. H2O has this shape where I have an oxygen in the middle, two hydrogens that are bonded to that oxygen through a chemical bond. Other examples that I have are sugar, C6H12O6. This is a little bit harder to draw, but it is made up of carbon, hydrogen, and oxygen molecules, or atoms, I should say. And then we have silver chloride. Silver chloride, which is another example of a compound. We see here that all of these compounds are made up of two or more types of elements. Water is made up of oxygen and hydrogen. Sugar is made up of carbon, hydrogen, and oxygen. And silver chloride is made up of silver and chlorine. The properties of compounds are going to differ from their uncombined elements. So silver chloride does not act like silver when we just look at an atom of silver. So that allows us to then differentiate compounds from elements through chemical experimentation. So let's jump into what atoms and molecules are just a little bit more specifically. An atom is the smallest particle of an element that has the same properties of that element and can enter into a chemical combination. So it can be used to create a compound, like we were talking about on our previous slide. A molecule, on the other hand, consists of two or more atoms that are again connected by strong forces known as chemical bonds. So we oftentimes refer to as molecules as compounds and atoms as elements, because you'll notice that these definitions are almost exactly the same as what we were talking about on our previous slide. So we can use these terms almost interchangeably, talking about molecules and compounds, and talking about atoms and elements, because an atom is one singular element, whereas a molecule is made up of multiple atoms, which is a compound. Here are some more examples of atoms and molecules. So we have on our first area here, hydrogen, oxygen, phosphorus, and sulfur. And what I would like to point out is with hydrogen, oxygen, phosphorus, and sulfur, we see on each of these images that there are actually two or more of those individual atoms that are attached to each other. However, these are still considered their elemental form because they are not compounds yet, because a compound is two or more different elements bound together. Some of our elements prefer to be bound with multiple atoms of that same element. So it just makes them more energetically favorable. So hydrogen likes to be bound with hydrogen through a chemical bond, but we still say that H2, because there's two hydrogens there, H2 is the elemental form of that molecule or of that element. The same goes for oxygen. It prefers to be O2 and bound through a bond between both of those oxygens because it's more favorable for oxygen to be two atoms bound together, but we still refer to these as their elemental form. On the other side, we have water, carbon dioxide, and glucose, which are similar or some of the examples that I was showing before, where we have different elements that are now bound together. So in water, as we said previously, we have an oxygen with a hydrogen on either side. We next have carbon dioxide, which has a carbon atom in the middle with two oxygens on either side of it. And then glucose, again, is made up of carbon, hydrogen, and oxygen, where we have these carbons in the middle, bound with some oxygens on the sides, and hydrogens that come off of them to fill their spaces. So here we have our elements, and here we have our compounds. After pure substances, we can then have a mixture, and a mixture is a physical combination of two or more substances that can be separated by physical changes. So a mixture, there are two different types of mixtures. There's a homogeneous mixture and a heterogeneous mixture. Homogeneous mixture means it is uniform throughout. We also refer to homogeneous mixtures as a solution because we typically see this in liquids. Examples of this would be something like seawater, which is made up of water and different salts, amongst other different minerals that can be found in the water, and something like apple juice, where we have water, sugar, and other flavorings that are put into that solution in order to make apple juice. But if we were to take samples of seawater and apple juice, when I say it's uniform throughout, these cannot be separated physically. So if I were to take a glass of apple juice, I couldn't go in with my fingers and pull out the individual particles of salt, or I'm sorry, of sugar, or of water, or of the flavoring. I wouldn't be able to physically separate the individual molecules that make up that solution. So that's why it is referred to as a homogeneous mixture that is uniform throughout. On the other hand, we have a heterogeneous mixture, which is not uniform throughout. And because it is not uniform throughout, this can be separated physically. Examples of this are trail mix, where we have, nuts, M&Ms, other things like that mixed together, and I can go in and pick out each individual piece of that trail mix and separate them into their different types: almonds, peanuts, dates, M&Ms, things like that. As well as chicken soup. We can separate chicken soup physically. We can go in and take out the individual noodles. We can go in and take out the carrots and the celery and the pieces of chicken, that are in that soup, and then we can be left with that broth. So, heterogeneous mixtures are mixtures that can be separated physically because they are not uniform throughout. We could go in, theoretically, with our fingers and pull out the individual pieces that make up that mixture. So, to summarize, matter can be separated into either a mixture or a pure substance. So we have a little flow chart here that we can use to kind of decide if something is a mixture or a pure substance. So we have some form of matter. We then have to answer the question, does it have constant properties and compositions? If it does, we go over to our pure substance. And we say, okay, this is a pure substance. It's constant properties and composition, so it's a pure substance. Then we ask, can it be simplified chemically? Can I break those individual bonds and be left with the same element or different elements? If it is the same elements, so something, if it can be or can't be simplified chemically, it would then be an element. If it can be chemically simplified, so I end up with two or more different elements, when I break those bonds, then it would be a compound. If when we're looking at the matter and it does not have constant properties and composition, let's change our color here, it would then be considered a mixture. So if it's a mixture, we have to ask, well, is it uniform throughout? Because then we can define it as either homogeneous, which would be uniform throughout, or heterogeneous, which would be not uniform throughout. So let's practice this. Let's practice using our chart. So this first question, asks us to classify each example of molecular art as an element or a compound. So we know we are already looking at a pure substance because it tells us to classify as either an element or a compound. Here, we have to then decide, can it be chemically simplified? Would I have two different elements if I were to break this down? Well, here I have these little molecules here that are the same element. And as we talked about previously with our examples, even if they are the same element, which in this case they are both hydrogens, okay, this looks like our previous example, this would then be considered an element. Okay, even if I broke those bonds, they would be two of the same element. There would be no other element present. In our second picture here, we have two different colors of elements being shown in our picture. In this case, it was our other example of CO2. So I'll try to draw this with the correct colors. We had C in the middle, and then there were oxygens on either side, and they're bonded together. Okay, so if I broke these bonds up, I would be left with two or more different elements, meaning this is a compound. Our second question here is asking us to classify each example as a pure substance or a mixture. So I'm looking to classify just up to here. So a pure substance is made up of the same thing, same molecule, same compound, same element, whereas a mixture is made up of two or more different molecules or compounds. So if we look in our first image, all of our molecules that we're seeing are the same. So if they're all the same, this is a pure substance. In our second image, we have, here again, there's our carbon dioxide that we saw from our previous example, but we also have molecules that are not carbon dioxide. So I have two different molecules or compounds in this image, so this would then be a mixture. So now that we can classify our matter as either a pure substance or a mixture, an element or a compound, a homogeneous or a heterogeneous mixture, we should now discuss the different phases of matter. So we've touched on this a little bit more, that all substances can either be a solid, a liquid, or a gas, but let's discuss a little bit more in depth what it means to be a solid, a liquid, and a gas. So the solid state is our first example. Oops. That's our first little flask here in our image. So a solid has definite volume and maintains its shape regardless of its container. So in our container here, we have our solid. It's maintaining the shape that we put it in there as. It's not expanding or taking up any other shape. It is simply keeping the same shape that it had before it was in the container. We can see from our little zoom in here that in a solid, all of the particles are in a kind of like a stacked or regular pattern, as we can see here. So we have, particle, 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 particle. They make up this nice little stacking pattern in order to be a solid. So in a solid, our individual atoms or our individual molecules are right next to each other, lined up perfectly. They are touching each other in a solid. So the atoms themselves physically can't move around. They are stuck together. There's no room for them to move around when they are in a solid. And that's why they're able to maintain their shape when they are in solid form. Now we can look at liquids. So let's look at a liquid here. Here's our second image. Okay, in the liquid state, those liquids still have a finite volume. When we're pouring something into a measuring cup, we then know its volume, but that liquid is going to take the shape of its container that we pour it in. So in comparison from our solid to our liquid, we can now see that we're taking up the shape of this flask that we are in. So, we have this kind of rounded bottom, so there's a wider portion of our liquid here and a narrower portion up there, so it's taking up the volume or the shape of its container. But even though it's in a container, we can still determine its volume. In a liquid, we can see that the particles are still pretty close together like they are in a solid, but they're not in that nice stacked pattern that we saw before. So what's actually happening is these individual atoms and individual molecules are free to move around, okay, and move past each other. So that's why we're able to take the shape of our container, because those individual atoms and molecules can move around and move past each other and kind of change the shape accordingly. So that's how we get that liquids are fluid, because they're individual atoms and molecules. Yes, they're very close together, but they can freely move around, so they have some fluidity to them. Our last phase is a gas, which is our last one over here. Okay, in the gaseous state, a gas has no definite shape, and it assumes the shape of its container. So we can see here in our gas that the individual particles are spread out amongst the entire flask that we are in. So a gas, when it's not in a container, has no definite volume, and when it is in a container, it assumes the entire volume of that container. So if this was a 250 milliliter flask, we would say that the volume of the gas is equal to 250 milliliters because it assumes the volume of its container. The particles in a gas are very far apart from each other and can move around freely without interaction with the other molecules or atoms that are in that gas. Sometimes they hit each other, but that's just because they're moving so fast. So another comment I want to make about the solid, liquid, and gaseous states is that as we go from one state to another, our molecules and our atoms are moving faster. So when do we observe this? Well, if we take a piece of ice out of our freezer and we put it into a pan on our stove, what's going to happen is it's going to start off as a solid, and as I heat it up, it's going to turn into a liquid. So I'm adding in heat, and that's going to change our molecules from a solid state to a liquid state, because those molecules are now moving faster due to the increased heat. Once that ice turns into water, the next thing that's going to happen is we're going to keep adding heat. And we know from just boiling water that we're going to go from a liquid water to steam, which is gaseous water or water vapor. And those molecules are now moving even faster, so fast that they can break free from the liquid and form the gas, meaning that they're moving so much faster and have a higher temperature to them. So let's think about that with this question here. In which of the following would the particles move most rapidly? So if we're talking about how fast the molecules are moving in relation to their temperature, well, if they're moving more freely, they have more temperature, they have a higher temperature, which allows them to move more freely and faster. So our four examples are ice, which is a solid, so the molecules can't move at all. Our next example is water, which is a liquid. So those molecules can move past each other, but they're still close together. So molecules, they're close, but they can move past each other. We then have steam, which we know is a gas. So in a gas, the atoms and molecules can move freely. And our final example is boiling water at 100 degrees C, which boiling water is still water, so our reasoning for B is the same for D. So which one are the molecules moving most rapidly? Well, that would then be steam, because those molecules are moving the most freely in comparison to our other three options. So the higher the temperature, the more rapidly those molecules are going to be moving. And that's because they have more energy to move around at higher speeds.